Good morning, everybody. I'm actually a minute early for once, so that may be why not that many people are here. Also, it's Friday, so. Okay. Oh, we got a chat. Okay, that's fine. If you guys have technical difficulties, it's all good. Okay, so other people will log on or not. That's on them. Couple quick housekeeping things. First is, yes, we'll still be on Zoom next week. I have to take a test, a COVID test between 3 to 5 days after my husband's official quarantine period ends Sunday. And then if that's negative, my doctor will clear me to come back to work. So Zoom again, woohoo! Yeah, and we don't know if my daughter's school's going to be open or not yet, or if she's negative. My husband is actually taking her right now to the doctor to get a hopefully negative COVID test. If she's still positive or her school is closed, it'll be fun. We'll figure out how that'll work because my husband does have to go back to work. Maybe my mom will come over and mask. I'm not sure. We'll figure it out. But my hope is that she's negative and that her school will reopen and we'll be good to go. So I will for sure be here on Zoom. The question will just be how many members of my family will also be in the house with me? So, we'll figure that out as we work through it. It's just, we're going to have to be nimble and flexible this semester and just do the best we can in general. This is why I put the contingency plans in my syllabus for the Zoom and whatnot, because I knew stuff like this would happen. If not to me, then to one of y'all. So I understand. Okay. Next thing, I'll go ahead and share my screen here. So I sent you an email about the groups and topics. And so what I did was create groups for each of the things that were submitted. And then I see that folks who were in the need to select a group category have been selecting them. This is a group project. I've had, I think, one person ever do it by herself, and she was very conscientious and it was still a lot of work for her. So I highly recommend you do group up. So if we need to even collapse some of these groups, that's fine, whatever y'all need to do. But I'd highly recommend the 3 folks who are floating down here to join an existing group. And again, some of these smaller groups may want to ponder combining, but 2 people should be fine. At least you have someone to share the workload with. So we will start having project work days for those after our next exam. Our next exam is scheduled for the 6th, which I believe is 2 weeks from today, a week and a half from today. And so I should be back for that. God willing, and the creek to rise. If I'm going to be super old fashioned, I should be back for that. I should be back on campus. We should be able to do that in person. That also means we'll be able to have our work day in person. So y'all can have me right there to work with you. So that means between now and then, for sure, you need to figure out your group and exchange contact info. If anyone needs me to give you someone else in your group's email, let me know. But we will go from there. So And just a reminder of what you are doing in the group project, because I think some people are getting a little like coming up with really good ideas, but those ideas are actually experiments rather than questionnaires. You are developing a questionnaire to measure one thing. And so I've been trying to help some of you kind of narrow that down, right? And so if you want to measure like this and that, you need to actually like come up with a measure that somehow combines the two, if that makes sense. So think of questionnaires you may have taken either for research studies here or just for like surveys you've taken for Kohl's or Target, right? Those are questionnaires. And so you want to be able to think about a topic you can easily write items for that will do all the stuff we've been talking about, right? Group together nicely for your reliability, have good validity so you know you're measuring what you're supposed to be measuring, all that good stuff. And again, I'll continue to give you guidance on this throughout the semester. All righty, so today we are diving back into more numbers. I know, some of you this freaks you out. But again, we are going to do the best we can with me being here, right? And I'll go slow. If we need to, stop and go back to things, we will. You'll have another homework assignment about this. If you haven't turned in the last homework assignment with the initial stat stuff, please feel free to submit it to Blackboard at any time. I know a couple people have emailed them to, and that's great. But do turn that in so that I can give you feedback and start to help you figure out where you are perfectly right, which I'm guessing a lot of you will be, and where you may be going wrong. So what we're going to talk about today is, okay, now that we've got these numbers, right, and we can do things like say, what's the average score of these, and what's the range of scores? Now, what do we do with them to make them make sense? When you have created your questionnaire and you've given it to your 30 people and you've got those pretty numbers sitting in front of you, what do you actually do with them? That's what we're going to start talking about today. All right, again, it'll be pretty helpful if you do have your book out ready to go. I've referenced the page numbers and the table numbers. Let's fix that real quick. Sorry, that's just going to bother me. Table. Nope. A different language. There we go. Table 7.1, for example, here. Okay. And again, I will be following along in my own book, but probably easiest if you have yours up to reference these diagrams as well. Some of them will be things you've seen maybe even lots of times before, for example, like the normal curve, or what's sometimes called the bell curve. All right, so you may hear these terms thrown around when you look at different types of assessments. Norm reference versus criterion reference. What the heck does that mean? Norm reference test is where you compare each person to a norm. You compare each person to a norm. What the heck is a norm? Well, a norm is a set of test scores in the peer group, which is often called the norm group. So basically, you are comparing, and that's what the referenced is here. You're referencing or comparing the scores to their peers, to that norm group. So you're saying, how does this person do compared to those of their colleagues around them, their fellow students, for example? Norm referenced can be great. They can also create competition, right? So if I were to say on the last exam, the average score was this, and you all should really be trying to norm reference to get better than that, right? You might be like, oh, I'm gonna do it, right? You might like gamify the class. And well, in theory, that could potentially create better scores. It could also create a type of animosity or competition that might not be conducive to supportive learning environment. Criterion reference tests describes where you are comparing them to a predetermined standard. So you're comparing the score to a predetermined standard or criterion. So you say, for example, were I to decide to get licensed in psychology, there's a big test I have to take called the EPPP. And when you take that, it is criterion referenced. You have to get, I don't remember, it's like a 70 or a 75 or above on the test to pass and go ahead to get licensed. That is a criterion referenced test. It doesn't actually matter how I do compared to my peers, right? I just have to meet that criterion, meet that predetermined standard. So it basically describes specific types of skills or tasks or knowledge that the test taker can demonstrate. So for example, you could also say, here's a criterion reference test for math skills, right? And if you get above a 80 on this, this means you have the basic math skills you need to join college classes. What you do then is you would use the results to make individualized programs of instruction for the person, particularly if you're using the test to make for diagnostic purposes, basically diagnostic purposes. There we go. Basically, you're trying to find, are there problems that can be remedied? And let's recognize those people who need help and get them that help. This can also be used to compare groups other than individuals to each other. So for example, the No Child Left Behind Act. I love that Google knows what that is and capitalizes it. But that was used to compare schools to each other. It was norm referencing with schools, right? And so partially because of that, schools would implement all kinds of these programs, right? Because it was within the school, within individuals, it was criterion referenced, right? You got to get a certain score to pass and to graduate. But among the schools, it was norm referenced, right? And so, for example, when this was really big, my husband was teaching at a school in Georgia while I was on my residency. And they decided for students who took their SLOs and didn't do well, SOLs, sorry, and didn't do well, they would put them in a remedial class. And so my husband was a math teacher. So you had the students who were worst at math, who hated math the most, who still took a normal full class period of math every day, would also have to come and work with him for another entire class period just on math so they could practice. I could see what they were doing. They're basically just trying to help those students pass. But like, I don't know that that's the best solution to criterion referencing, right? Like those kids were miserable. And obviously that made my husband miserable as well, because as much as you try to motivate and support, if they just don't want to be there and they're forced to do double of what they hate, it's problematic, right? Okay. So if you have your book and you look at page 129, there is a box or a table that references some of the things that are norm referenced and some of the things that are criterion referenced. So things like the GRE, the SAT, the ACT, the MCAT for med school, those are all norm referenced. So they're based around a norm. The IQ test that we'll talk about in a couple of weeks, those are also norm referenced. So those are based around, and for our IQ test, it's usually the mean is set at 100, and then the standard deviation is set at 15. And so they always sort of renorm the test every year to make sure it's hitting that, or every time they revise it. Personality inventories are this way, career inventories. college exam scores that are graded on curves are this way because it's relative to other people in the class. Criterion reference things. Example, your driver's license test, right? You pass or you don't. You need a certain score and they let you operate a vehicle, or they're like, we do not want you on the road, share from Clueless, right? Your college entrance exam, right? If there was like an actual exam you had to take for writing. I think we were doing this at one point. I don't know if we're still doing it, right? But that would be, there's a score you got to get. The BDI-2, Beck Depression Inventory. This is one of the most widely used questionnaires of depression. And it has a criterion. It has a cut score. Above this cut score, you are considered to be clinically depressed, and we should definitely give you therapy. Not that you can't give someone therapy who's below the threshold, but that's where we really start worrying about people and making sure they get therapy. Alrighty, so you can also have what are called derived scores. So we've got all the stuff we've looked at already, right? We've got our raw data. We now know how to get the mean from it and the standard deviation. That can tell us a little bit about it, but we can also take that and we can convert it to other types of scores that have meaning in different ways. And we're going to start going through those here. So the first, and probably the one you've heard of the most often, honestly, are percentiles. So this is the percentage of people falling below the obtained score, and it ranges from 1 to 99, and 50 is the mean. So this is like, if I, was at the 80th percentile, right? That would mean based on my score on this test, 80% of people or 79% of people did worse than I did, but that means, the other 20% of people did better than I did, right? So again, if you've taken the sort of achievement tests, multiple choices that they give you in school and gotten scores back, they typically are in this type of percentiles. They also do percentiles for things like height. So if any of you have kiddos or younger siblings or remember this from growing up, they have these height charts and they'll tell you what height you are, what percentile you are. And I think when you get to be like 4 or 5, they can start to use that data to like project out how tall you'll be. So for example, even though I am average height 5'4", and my husband is average height 5'10", my daughter has consistently been above the 90th percentile, and at times she's at the 99th percentile for her height. Not sure where she got it, right? But it just means she is taller than, let's say, 98% of kids her age. In fact, at her 3-year appointment, she was the same height as the average 4-year-old. I don't know why. I don't know where she got it, but that's an example of a percentile that's used more commonly. Percentile doesn't mean percent correct, right? So it doesn't mean you got a score out of 100, right? And that this is how many you got right. And again, I think height is a really nice example for that, right? It doesn't mean that my daughter is 90+% right on height, right? She's not correct on her height. She just happens to fall, that place relative to her peers, basically. And so we did percentile ranking when we were looking at our numbers last week. And if you look at figure 7.1 in your book, it's a pretty normal curve. And the percentiles are down at the bottom there. Those are the percentile scores. And what you'll see when you look at that is that the percentile scores really cluster around the mean. And that's because of the characteristics of the normal curve. If you look at the middle of the normal curve, right, it is a bell shape. And so that means, and this, where you are high to low on the y-axis tells you how many people fall there. And so a lot more people are around the average than at either end. So you're going to get a lot more people. So a lot more of the percentiles will sort of cluster right around there. All right, these are all of the types of standard scores. There's a lot. As with all of our previous PowerPoints, we are going to go over each of these on its own slide. So you can kind of like give yourself a little bit of a breather as we go through here. And we'll start with Z-scores. Z-scores transform data into standardized units that are easier to interpret. Basically, what Z-scores do is they translate the mean to a 0. And then you are either a number of Z-score points above the mean or a number of Z-score points below the mean. So practically speaking, Z-scores run from -4 to +4. And so you can see the Z-scores on this line here. So again, you set the mean at 0, and then 1 standard deviation out from the mean, you're at +1 Z-score. 1 standard deviation below, you're at -1. So it's a standard score that helps us understand where they fall on the normal curve. And basically, it allows you to just say where someone's score is relative to the mean pretty easily, right? So if you can say, well, this person's Z-score was +2. Well, we know that they are 2 standard deviations above the mean. So they are better, more, right? Whatever criterion you're looking at than the mean. So like my daughter, I believe, is actually somewhere out here, like between a 2 and a 3 Z-score for her height, right? Because if you look at like percentages, that matches up. So when you do look at this normal curve, the x-axis down here, the horizontal one, is often indicated in Z-score. So when you see diagrams of normals of a normal curve elsewhere, what you'll often see along the bottom is Z-scores. Okay, so if you've ever seen, like, why is the mean 0, they were probably using a Z-score. So the mean is 0 when you transform something into Z-scores, and the standard deviation is 1. And again, that just makes it easier to conceptualize than, you know, say when we did our heights, right? And the standard deviation and mean were both things with decimals, right? So it's just a little bit easier to conceptualize. And then the nice thing is, if with Z-scores, let's say we look, you know, 1 standard deviation below the mean and 1 standard deviation above the mean. So this middle section of the normal curve, right? The mean of scores around the mean is always, or the sum, sorry, of the scores around the mean is always 0. So that makes sense, right? If we're adding the same positive numbers and the same negative numbers, that's going to come out to be 0. So again, this chart I like a lot because it also gives you some ideas about percentiles, right? So a score that's 1 standard deviation below the mean is about at the 16th percentile mark, right? 15.9. Score that's 1 standard deviation above the mean will be at the like 84-ish percentile rank. Okay, so you can start to see how these things all map on together. And basically, the way that you get it is it's sort of an area under the curve, right? So we're just accounting for all these people. Remember, this, everything on this axis is like the number of people who have that. And so for that reason, if I were someone who could magically just add up what this area is, right, then I could just add up all the people in each of these parts of the curve, and that would give me 84 or for being precise, 84.1% of people, right? So you can use what we've talked about so far to actually take raw scores and put them into percentile scores. And we can also do some calculations to change something to a z-score. So here is the fun part where, believe it or not, this little box is supposed to be a formula. So let me go ahead real quick here and open my original PowerPoint. This is what happens when you convert things. And then you'll be able to actually see all the scientific symbols and whatnot. Yep. Yeah, it's a formula, and it's actually not even a picture of a formula. So I'm not sure why I didn't copy. So let me actually just try to, oh, you know what it is? This just got moved in front of it. Haha, okay, I feel better now. There we go. Ta-da! All right. So to find your z-score, to calculate a z-score, you take X, which is that person's score. So again, let's think about heights, because I think they're just the easiest to try to conceptualize, right? It doesn't get confusing with, you know, is it right or is it wrong, right? So to find a z-score for height, we would take, again, let's take my daughter's height. I think she's about 40 or 41 inches now, right? So we take her height would be X, the 40 inches. We would take the average height for a 3-year-old. That's that mean, right? Which I don't know what that is, but I can probably find it out pretty quick. And I'm gonna do, let me Google that real quick. Alrighty, so average height is somewhere from 34 to 40 inches. That doesn't really help. What I'd really like is the actual average, because I need 1 point. See if someone else. There we go. Maybe. They're gonna give it in ranges because they don't want parents to freak out. Like I know what they're doing. Here we go. 3 years. For girls, 3 feet 1 inches, which is 37 inches, right? So again, here I would, and I'll type this in the chat. So X here is my daughter's height, which is, let's say she's 40 inches. She might be 41 now. Who knows? Our mean here is the mean height for a 3-year-old. In this case, girl. And in this case, they're saying that's 37 inches. Now, I don't know if I'm going to be able to find the standard deviation for height. Let me try to find it. They're going to be like, who is this person? Why is she Googling this? Maybe the CDC growth chart should help me. Traditionally, we would have calculated this, right? So let's just pretend we know the standard deviation, and let's say it's 2 inches. So SD equals 2 inches is the SD for height for a 3-year-old girl. Okay. So then what I could do go to my nifty online scientific calculator, right? So we've got, I'm writing myself, X minus M equal over the standard deviation, right? So her height is X. So 40 minus 37. Okay, that gives us 3. And then again, let's use the standard deviation of 2. Okay, so she would be 1.5 if that were the case. I'm guessing the standard deviation is different, but that's okay. But let's say that this is correct. So what would happen here is that, okay, a z-score of 1.5, right, would put her somewhere in this range. Actually, that might be accurate. Now that I look, because sometimes she's more in the 90th percentile. So yeah, so if she's at a 1.5 z-score, right, then she would be somewhere in the 90 to 95th percentile. Okay, so yeah, and again, that just tells me something about her height relative to the average height for kiddos her age. Okay,
It's 1.5 standard deviations away.
Yep, exactly. So a z-score of 1.5 means it's 1.5 standard deviations away. Exactly, Troy, you're spot on. Yep, and it's away from the average or the mean. Yep, yeah. And so it basically just tells us how they are relative to other people in the way that her height doesn't if I just tell you she's 40 inches, right? Like without context, you're like, is that tall or is that short? Right? So like, I am 64 inches, right? So like the 40 inches could seem really short to me. It's not, right? Okay, so about z-scores. Z-scores are golden. So what this means is z-scores really help us see where an individual's raw score falls on that normal curve. Give me just 1 second. I don't want to blow my nose in y'all's ear. All right, I'm back. So like I was just saying, it helps us to see where an individual's raw score falls on the normal curve. It's helpful to convert the raw score to other types of derived scores we're going to talk about as well. And so this is why your book says that z-scores are golden and can help us understand the meaning of scores. There are also times where when I'm doing statistics, for example, I might choose to convert to z-scores, right? So for example, in my dissertation study, I measured how people felt about their bodies, but then I also measured behaviors they engaged in related to their bodies. So were they like weighing themselves a lot? Were they checking for fat on themselves? Things along those lines. And those are both measures of body dissatisfaction, but they're on completely different metrics. They're scored completely differently. But by turning them both into z-scores, that put them on the same metric, right? So each person's score now became just their deviation from the mean. And then that meant I was actually able to combine them to create a composite score of those two things. So z-scores can be really helpful even when you're doing advanced statistics. So again, this is just really helpful to look at and see all these different types of scores. We'll talk about t-scores in a minute as well. So you can take a z-score and just convert it to a percentile, right? So you would find your z-score and then either approximate your percentile or in your book. And let me make sure, I think I changed these appendices numbers because they did switch up a little bit, but let me make sure I am telling you accurately which one it is. It is Appendix F. So that is on page 329 in the back of your book. There is a whole table of if you are this z-score, here's your percentile, right? Here's your percentile. So again, let's look at my daughter. She is, let's say 1.5 standard deviations above the mean. Her z-score is 1.5. So her percentile for height would be 93.32%. Okay. So that gave us information we can kind of understand much more quickly, right? Because percents just make sense to us as humans. We talk about them a lot. We use them to quantify things a lot. So we could look at, other examples right? If we were just going to practice using this table. So for example, let's say I had someone whose Z-score was at 2, then their percentile rank would be a 97.72. And if you look at the Z-scores on those charts, what you'll notice is as you get bigger and bigger Z-scores, the percentiles get closer and closer together. And that's because of the normal curve, right? The percentiles kind of clump up at the ends here because there aren't as many people at either extreme, right? There's many more people in the middle of the bell curve. So for example, comparing a Z-score of 4, which is 99.997%, and a Z-score of 5, which is 99.999997%, right? It's almost meaningless in the grander scheme of things. You also can use this table to convert a negative Z-score. So for example, if someone was at a negative 1.2, their percentile would be the 11.5% percentile. That sounds redundant, but and we actually have friends whose kids are about Quinn's age who are on that end of the spectrum. So it's really interesting to see 2 kids who are the same age, right? But their heights are like this because they're at the other ends of that bell curve. So again, these standard scores and the percentiles just allow us to say, where is this person relative to other people, basically. So if you look on page 132 of your book, they just show just the Z-scores on the normal curve, basically the diagram we've been looking at on the PowerPoint. All right. Now we're going to start to talk about standard scores. And standard scores, how do I put this nicely? Standard scores are the somewhat arbitrary scores that test manufacturers come up with that they want to put people's scores on. So I was just talking not too long ago about the IQ scores, right? IQ scores having that mean of 100 and a standard deviation of 10 in either direction. Why? Why did we choose a standard deviation of 15 in either direction? I think I said 10 because I want it to be 10. Yeah, why didn't we choose a standard deviation of 10 or 25, right? It's admittedly a little arbitrary and they do have reasons, right? But it's just something they choose. When we talk about the personality tests, a lot of them are on a metric where the mean is 50 and the standard deviation is 5. Again, why? Why choose that one, right? I don't know. It's just what people have chosen. And so standard scores are these. Other good examples are the SATs, right? Why is the average on an SAT 500 and the standard deviation 100? I don't know, right? And the GRE used to be on that metric, but now they changed it. So it's on a metric I literally don't understand. I don't know how to interpret for my students because it doesn't make any sense to me. The average is something random, like I think 143 or something. That's not right, but it's something like that, right? Why? I don't know. If anyone took the ACT, the mean of that is 21. Who decided that made sense? The people who make the ACT. So standard scores are not going to make as much sense as Z-scores, is what I'm saying, basically, because they're things that someone in charge, hopefully some data scientist, but who knows, could be the marketing company, right? Marketing part of the company, decided this is what our average should be. This will make all sense. And sometimes you're like, to whom, right? Okay. But there are a bunch of these different standard scores. The nice thing is, as soon as you have your Z-score, it's pretty easy to do this, okay? So you have your z-score, and let's just keep using my daughter's as an example, her z-score of 1.5, just because it's a nice easy number to calculate things with, right? And I'll throw that in the chat so y'all have that too. Z is 1.5. Oh, helps if I'm actually in the chat. Let's take a look. So those t-scores, these are the ones I was talking about. Oh, sorry, the standard deviation is 10, not 5, because that makes sense. So we're basically just going to use this formula we just looked at. Hang on, I scrolled too far forward, where we take the z-score times the standard deviation times SD desired score. And then we're going to add the mean of the desired score. Again, I'm putting that in the chat for you. I love that I called it z-score. I'm going to stick with that. I think I should like trademark that. So in this case, all right, the mean for t-scores is 50. The standard deviation is 10. So if I wanted to take Quinn's z-score of 1.5 and convert it to a t-score, I would take 1.5 and multiply it by the standard deviation, which is 10, and then add it to 50. So that would be 15 plus 50 equals not 10, 50. Can't type and talk at the same time. Equals 65. Okay. So that is her t-score. Why do we need to convert it to that? I don't know. Someone decided that's the metric we're using for personality tests, right? So maybe it doesn't make sense for her height, but it's a nice example. Okay. DIQ scores are those IQ scores that I've been referencing. And they use a metric of a standard deviation of 15 and a mean of 100. So if I wanted to, for some reason, convert my daughter's heights to a DIQ score, doesn't make sense. We're just using an example, right? Then what we would do is we would take, again, her z-score of 1.5, and we're multiplying it by the standard deviation, which here is 15, and adding that 100, right? And so I need to just pull up my calculator real quick because I can't do 1.5 times 15 in my head. Okay, that's 22.5 plus 100, which is 122.5. Okay, basically, again, I'm going to keep bouncing back a little bit just because I think it's easier to try to explain on here. So basically, what you're doing when you are doing these calculations using this formula is you're taking your z-score, which again is going to fall right here, right? So she's about here, 1.5. You multiply it by the standard deviation of whatever you want to convert it to, because your z-score essentially is the standard deviation it's away from, right? So, but then you need to say, okay, what is the standard deviation on this metric, right? So in this case, it's 10. This is actually t-scores at the bottom, so it helps to do it. Okay, so we did that. Yep, that makes sense, right? That if she's at a 1.5, we multiply that by 10. That gives us a standard deviation for this of 15, gives her a score of 65 when we add it to that mean of 50. Okay, and again, fully acknowledging these are super random, right? But it helps to conceptualize why and how scores get converted when we look at them this way. Let's do another example. So stainings might make less sense to me than any of these, to be perfectly honest. Okay, so stainings are what's used for your individual subtest score on an intelligence test. So your overall score on an intelligence test will be on this mean is 100, standard deviation is 15. But each of the subtests you take to get that total score is on a staining, or staining, I think it's staining. Okay, so let's go ahead and do this. So again, we got a z-score of 1.5. We're going to multiply it by the standard deviation, which here is 2. And then we're going to add it to the mean, right? So 1.5 times 2 is 3 plus 5. And that gives us a standing of 8. Okay. These are also used on achievement tests as well. And if you look at these figures that I've referenced here in the book, so for example, if you look on page 135 at figure 7.5, it shows you number lines for the z-scores and how those compare to those staining. So again, just like a helpful references. Well, that one was percentiles. I had the wrong one for staining, guys, sorry. But it's in there. Alrighty. Keep going. STEN scores are used with shorter personality inventories and questionnaires. Again, same thing. We're going to use STEN scores. We've got 1.5, because at least the standard deviation is the same, right? Of 2 plus 5.5 in this case. Okay, so 3 plus 5.5 is 8.5. We just calculated a STEN score. Okay, we'll do the NCEs. These are like percentiles, but they basically range from 1 to 99. But they're evenly distributed instead of being on that normal curve around the mean. So this can be used for educational tests as well. All right, so here we again, 1.5 is our z-score. Oh, I should say NCE. You all know what I'm doing. So 1.5 is our z-score. Going to multiply that by our standard deviation of 21.06 plus 50. That's our mean. Alrighty, so using my trusty computer calculator off to the side. Nope, hang on. Helps if I use a decimal. There we go. Okay, so that's 31.59 plus 50, which would be 81.59 would be the NCE score. We could do the same thing and put it on the SAT metric. Okay, so z-score of 1.5 times our standard deviation here is 100 plus 500. Okay, so 1.5 times 100 should be 150, right? Yes. I'm just making sure my brain is working today. Yes. Okay, so then we have 150 plus 500, and that is 650. Okay. And then let's say we'll do the same thing with the ACT. So ACT, we've got 1.5 times the standard deviation. Here is 5. People like to use 5 for standard deviation, plus the mean of 21. Okay, so 1.5 times 5 is 7.5. You won't need to remember. I will give you these numbers on an exam. You won't have to memorize them. And on homeworks as well. Good question, Debbie. 7.5 plus 21 would be 28.5. Boom. Pretty good ACT score. So these are like the standard scores we've just worked through. But as you can see, there's also the sort of more arbitrary one, even more arbitrary than we've already talked about. What? I'm just showing you, I'm sorry if my sarcasm's too much for this early in the morning, but it's just, they're all very arbitrary. They're all like some person decided somewhere, and it may or may not have been a scientist who did it. So, yeah. So one of your next assignments, once we work through this, that we'll do in class is to practice doing some of this stuff, practice these conversions. As you can see, and again, to answer Debbie's question, yes, I will always give you the means and standard deviations. You do not have to memorize those. I will also give you formulas, and it would just be about you, what some of my professors used to call plugging and chugging. Just put the numbers in and get the values out. So again, just to understand what these are, what they do. So we will pick back up on Monday, keep going through this lecture, and then we will start to do a little more on types of error and things like that beyond the standard deviation. And like I said, at some point next week, we'll do another assignment as well that's a little math. So I'll stick around for a minute in case anyone has any questions. Take care of yourselves and have a good weekend.